Hello, I am Taeyeon from PostTech Korea. Today I'll be presenting our work that leverages relational patterns and images for few-shot classification. This work is done by Taeyeon Kang, Hee-seung Kwon, Jo Hong-min, and Min-soo Cho. The task of few-shot image classification is to learn new visual concepts from a small number of images. For example, in a 5-way one-shot setup, we're given a labeled image for each class, which we call a support set. Given this support set, we want to classify the query image. In this example, the answer is the second class. One of the important points of this few-shot classification is that the target classes that we are interested in are completely unseen during training time. So a few-shot learner should understand novel visual concepts online at testing time. To better recognize an unseen class object, we propose a convolutional process that first captures what to observe and then predicts where to attend on the novel object. First, given a base feature map from a CNN, the self-correlational representation module extracts structural features from an image self-correlation and transforms it to a relational descriptor. Second, the cross-correlational attention module takes an image cross-correlation and then gives co-attention to the pair of object regions. Finally, the image embedding becomes a metric-based classifier for computing semantic similarity between the query and the supports. Each of these modules extract feature from either a self or cross-correlation to form an image embedding, so we call it as Relational Embedding Network or RENet. I'll talk more about each process in the following slide. Given a pair of a query and one of the support images, a backbone network F provides a base representation Z. Z is transformed to a self-correlation tensor R by computing self-correlation between each of H by W feature vector in Z with its neighborhood. And this relational pattern is analyzed in a convolutional manner and then added to the Z to form a self-correlational representation F. This relational descriptor suppresses appearance variation and reveals structural patterns such that the model can better understand what to observe within an image. Next, a pair of representation is transformed to a cross-correlation. The cross-correlation is again refined in a convolutional manner to form cross-correlational attention maps. This process analyzes the geometric patterns in the semantic correspondence between images and generates co-attention map such that the model can explore where to attend in the context of a support image on the fly. The attention maps give special attention weights on aggregating F to generate image embeddings. This overall process is applied to all support images in parallel, and then the query is classified as its nearest support class. We compared RENet with other methods on 4 standard few-shot classification benchmarks on both 5-way one-shot and 5-way 5-shot setups. RENet outperformed the recent state-of-the-art methods. We evaluate the effectiveness of each proposed module on the 2 representative datasets. The 2 proposed modules consistently improved the baseline. We also provide qualitative results to study the effect of each module. The results demonstrate that the self-correlation representation module can activate relevant feature within an image. For example, you can see the activation of a building behind the truck increases. The subsequent cross-correlational attention module generates co-attention map that focus on the common context between the query and the support. For example, you can see the athlete's hand holding the bars are attended in both images. To learn more about analysis, ablation studies, and qualitative results, please refer to the paper. And if you'd like to use RENet, please visit our GitHub. Thank you.